So in this video, we're going to talk about Hess's law, okay? And what is Hess's law? Hess's law allows us to calculate the enthalpy change for a reaction to be based on known enthalpies of reactions, okay? So I usually call this a target reaction, okay? And it's usually you're given a reaction and you're given several other reactions in which you got to calculate the enthalpy from those several other reactions of the actual target reaction itself. And so how do you go about solving these types of problems? Well, let's go through my steps of how do we solve these problems, okay? So again, we usually consider whatever you're targeting, the target reaction, that's what you want to get, okay? And the idea is that how do we calculate the enthalpy of this reaction? We're going to manipulate these reactions like math and actually solve for them. So here's a general procedure. The first thing I do is look for the first thing that comes in the reaction, in the target reaction. And so in this case, I see that 2 moles of copper solid comes first. So I look at these reactions. Now, I'm going to be very particular here. 2 moles of copper solid comes as a reactant, okay? As a reactant, okay? So as a reactant, I have 2 moles of copper solid. So I'm going to look in any one of these 3 equations and say, okay, where do I see 2 moles of copper solid as a reactant? And so in this case, in this first equation here, I see that 2 moles of copper solid appears as a reactant. So in that case, the reaction, I'm just going to write this straightforward doing the math. So this is 2 moles of copper solid plus sulfur solid, okay? That's going to give me this product. Now I'm also going to write the change of enthalpy. Nothing changes because I did not manipulate the equation, so this is just negative 79.5 kilojoules, okay? Now what's the next thing that comes in the reaction? 1 mole of oxygen gas, okay? So 1 mole of oxygen gas comes as a reactant. 1 mole of oxygen gas comes as a reactant, okay? Well, where do I see 1 mole of oxygen gas as a reactant? I see 1 mole of oxygen gas as a reactant here, but we got to be very careful. Notice that the product is actually SO2 gas. The product here is copper 2 oxide, okay? And so using this equation will actually not work. And so what if I actually use this one? Now, again, bear in mind, this is 2 oxygen gas, but again, this is how we got to think, okay? If this product was just straight up 2 moles of copper oxide, then we could say, okay, well, that's fine. But because the product is different, we actually, it's not best for us to use this first. And so if we go ahead and use the third equation, then this becomes copper 2, so this becomes Cu2s solid plus 2 moles of oxygen gas. Okay, and that goes to 2 moles of copper 2 oxide gas plus SO2 gas. Okay, and notice that I did not change anything. So again, my change in enthalpy stays the same. So this is negative 527.5 kilojoules. Okay, well, notice that the overall reaction has 1 mole of oxygen gas, like as a reactant. Remember, we did not use this third one here. And so the idea is maybe I could flip this backwards, okay, to give me the oxygen gas as a product, and those will cancel each other out on either side of the equation. So I'm going to show you what do I mean. So the last equation for us to use is the second equation here, but I'm going to flip it. So I'm going to say I'm going to put SO2 gas now as a reactant, okay, and its products are going to be sulfur solid plus oxygen 2 gas plus O2 gas. Now the idea is whenever you flip the equation, the sign of the delta, the enthalpy change. So this is now a positive delta H, which would be positive 297 kilojoules. Okay, and the idea is whenever you're done, finish manipulating the equations, these equations, they should add up to just these equations. So let's see. Okay. As a reactant, I have 2 moles of copper solid. As a product, do I see 2 moles of copper solid? 1 2 1 2 1 2 1 1 2 1 2. So there's no moles of copper solid on either on the right hand side. So this stays. We can't cancel this. How about sulfur? We see sulfur as a reactant over here. As a product, do we see it? Sulfur. Yep. So there's a sulfur as a reactant here. So the idea is this cancel. This cancel. And maybe I should write this out so we could see. So let's write out all our reactants. So this is 2 moles of copper solid plus sulfur solid plus, we're writing out all our reactants here. So Cu2S solid. So everything on the reactant side in all equations. So, and this is a +2 oxygen gas, okay, and plus SO2 gas, okay. So these are all the reactants. So 1 2 3 4 5. We have 1 2 3 4 5, okay, and these are going to the products. Well, I'm going to write everything on the product side. So this is Cu2S solid plus 2 moles of CuO solid. So 1 2 3. We also have SO2 gas. So this is SO2 gas, okay, plus, I crossed it out, but I'm just going to do it here. So this is sulfur solid plus O2 gas, okay, and these are all our products on the reactant side. So again, now it becomes much more easier for us to see. So whatever I have on both sides of the equation, I'm just going to cancel. So I see that a sulfur and a sulfur exist. So these will cancel on both sides, okay. What else do I see that I will cancel? Well, notice that I have 2 moles of oxygen gas over here. I have 1 over here. And so in fact, this will go away, but I will lose one of these. And so I'll only leave with 1 mole of oxygen gas. Okay. Well, what else do I see on either side of the equation that will actually cancel out? Well, I see, let's see. So we have SO2. So look, we have SO2 gas on both sides. So we actually have SO2 gas on both sides. So SO2 gas will go to 0. Okay. And what else do we see on both sides of the equation? Well, I see 1 mole of Cu2S, and I see 1 mole of Cu2S as the product as well. And so if I add this together, well, notice I can't cancel anything else. Okay. So if I look at what's remaining, I have 2 moles of copper solid plus, well, these go to 0. We have 1 mole of oxygen gas left. Okay, as a reactant, well, nothing less over there. And so as a product, we only have 2 moles of copper 2 oxide solid. Okay, notice that everything cancels out. And this reaction is actually the target reaction that we was looking for. So how do we calculate the change in enthalpy? Well, we'll simply just add, if in fact we get the target reaction, we simply just add the values that we just simply add the values that we calculated. And so in this case, the change in enthalpy of the reaction is going to be negative 79.5 kilojoules plus 297 kilojoules plus a negative 527.5 kilojoules. So all we're doing is just adding these. And so when I add these together, I should get approximately negative 310 kilojoules. Okay. So this would be my answer. So this would be the delta H of the reaction. Okay. So that's a general idea of Hess's law. So let's look at one more problem very quickly. So how about this one? I'm given this one and I'm asked, okay, well, what is the delta H for this reaction here? Okay. Well, again, let's go through the process. Okay, the first thing I see is Fe2O3 as a gas, okay, as a reactant. Well, if I look at 2 of these equations, there's only one place that this appears, and it appears over here. Now, it is a product. It is not, in the target reaction, it appears as a reactant. Here it appears as a product. So I'm going to flip this. So if I flip this, now I have 1 mole of Fe2O3 gas, and that appears as a reactant now, and its products are 2 moles of iron solid plus 3.5 moles of oxygen gas. Okay, but now remember, if we flip the equation, the sign of the delta H changes, so this now becomes positive. So the change in enthalpy of this reaction is actually positive 824.2 kilojoules. Okay. Now what is the next thing we have? We have 3 moles of carbon dioxide as a reactant. Okay. Well, we just used this equation, so this equation is no longer valid. We can't use. The only one for us left with is actually this. Okay. And so if we take a look at this, well, carbon monoxide appears as a reactant here, but notice we have 3 moles here. We actually don't have, and we have only 1 here as a reactant. And so the idea is that I could actually multiply this equation by 3. And so if I look at this, I'm going to do 3 times CO2, carbon monoxide gas. And what happens is that I got to multiply this. No, this is 1/2. I'm sorry, but I'm jumping ahead of myself. So this is 1/2 oxygen gas. And this is CO2 gas. Okay, and what happens to the delta H of the reaction? It actually multiplies by 3 also. So this becomes 3 times negative 282.7 kilojoules. Okay, so when I multiply by 3, this whole thing, the whole reaction and the delta H actually multiplies. Okay, so if I rewrite this, I have iron as a gas, 2 moles of iron solid, plus 3.5 moles of oxygen gas. And we know the delta H of this reaction is plus 824.2 kilojoules. Okay, now multiplying everything by 3, now we get 3 moles of carbon monoxide gas. Okay, and remember this is a 1/2. So if I multiply 3 by 1/2, well, that is just 3/2 or 1.5. So this is 3/2 moles of oxygen gas, and then multiply 3 by carbon dioxide. So this gives me 3 moles of carbon dioxide gas. Okay. And then simply, if we multiply 3 times negative 282.7, we're going to get what? Negative what? 84.81 kilojoules. Okay. And so this is being multiplied by everything by 3. Now let's add the reactions together and see what do we get. So we have Fe2O3 gas as a reactant, plus 3 moles of carbon dioxide gas as a reactant, plus 3.5 moles of oxygen gas as a reactant. Now as a product, what do we have? We have 2 moles of iron solid plus 3.5 moles of oxygen gas. Okay. Plus as a reactant, we also have 3 moles of CO2 gas. Okay. And now we're looking to just cancel. So I see that I have 3.5 moles of oxygen gas on both sides. So these will cancel out. Okay. And notice that I have nothing left in common. Fe2O3 is not on both sides, so we can't cancel that. Carbon monoxide is not on both sides, so we can't cancel that. And then there's nothing else to cancel it. So if we look at this, we're left with Fe2O3 gas plus 3 carbon monoxide gas. Okay, and that goes to 2 moles of iron solid plus 3 CO2 gas. Okay, now look, is this the reaction that we got? It's exactly the target reaction. Okay, and so if that is true, then we just simply add our enthalpies together to get the delta H of the target reaction. And so in this case, this would be 824.2 kilojoules minus, so again, we're going to add them. So it's going to be plus minus 848.1 kilojoules. And essentially, we're subtracting these. So the answer, if we subtract these, the answer should be around negative 23.9. The answer should be around negative 23.9 kilojoules, approximately around that. And this would be the delta H of the reaction. So again, this is how we deal with Hess's law problems.